It's my great pleasure, privilege to be able to introduce Professor David Norris from the Mechanical and Process Engineering Department at ETH Zurich for today's colloquium, the first one of the new year. Thank you all for coming. So just a brief introduction, because David has a lot to tell us. So David obtained a degree in chemistry from University of Chicago, then moved to MIT in 1990, I believe, to start grad school, where he joined the very new research group of Munji Bawendi, who was just starting as an assistant professor. So it's always very risky to start your PhD with a group that doesn't exist yet, if you're a first-generation PhD student. But together with Christopher Murray, the three of them, they very quickly developed new techniques to synthesize colloidal nanocrystals, which is the hot injection method that is now widely used. So this early work also led then to the Nobel Prize for Munji Bawendi in chemistry, 2023. Yeah, David's contribution to that was really to do all the spectroscopy and everything of the degeneracy of the nanocrystals that were possible to study for the first time. After that, he went for a postdoc to UCSD for 2 years to work with W.E. Murner, who also ended up winning a Nobel Prize in 2015. So of course, the obvious joke is that if you want to win a Nobel Prize, you should hire David. After he worked at NEC labs in Princeton for a few years, starting to work more on photonics, photonic crystals based on colloidal quantum dots, and in 2000 moved to the University of Minnesota first as an associate professor, then as a full professor, getting into plasmonics. And I think, here there's a lot of people working on theory of plasmonics. So I think the template stripping technique, which is going to be part of this talk as well. So template stripping, making ultra flat silver surfaces, achieving propagation lengths that theorists can only get when they use lossless silver, was really a huge breakthrough in that respect. So this attracted the attention of ETH Zurich, and in 2010, David made the move across the Atlantic to start his group, which is the Optical Materials Engineering Laboratory, where he has been since. Many additional advances, magic-sized nanocrystals, and Fourier surfaces, which is what David will be discussing today. Many awards, I'm not going to talk about all of them. I think the most important one, at least from my perspective, is also to highlight the Credit Suisse Teaching Award. David is known as a very good teacher. I personally have experienced his mentoring role, for which I'm very grateful. David, thank you for coming, and the floor is yours.
Thank you very, very much for this maybe overly kind introduction. I hate it when people talk about my teaching award, because it immediately raises the expectation for the talk. But anyways, I'm very happy to be here. I jumped at the opportunity to visit you all. And I'm going to warn you, this is the first time I'm giving a brand new talk that I made last weekend. So I apologize if it's a little bit rough, but I wanted to talk about some brand new results. And the question I want to get at is, can we make a new type of pixel, and the pixel that you're all thinking of now, a new type that can generate and sense arbitrary light? And I'll explain what I mean by that as we go along. Let me just start with an introduction to remind you that, of course, light is an electromagnetic wave, and a standard picture like this that you can find in a textbook, where you have an oscillating electric and magnetic field. But I just want to point out the parameters we need to describe this. We have the amplitude of the electric field. We square that, we get the intensity. We have the phase of this wave, its polarization vector, that the plane that the electric field is oscillating in, of course, the wavelength that gives us the color, and then the direction of propagation, which can be defined as the wave vector k, which I'll come back to in a second. And the reason I want to point all of this out is that, of course, with all these parameters, light can carry a lot of information. We are exploiting some of that today with like internet traffic, but not all of it. And we're going to get into that a little bit, hopefully, in this talk. So electromagnetic fields can carry lots of information. Now, in addition to that plane wave, which we will use some today, we can also confine electromagnetic waves, for example, in a thin slab of dielectric or semiconductor between two cladding layers. We can send a light wave in this thin layer. We get what are called slab waveguide modes that satisfy the boundary conditions for basically the light to totally internally reflect as it bounces back and forth, which I can't do very well here with my pointer, inside this dielectric. So with semiconductor thin films, we can make confined light. And also with metallic interfaces, so Ferry mentioned plasmonic, so at an air-metal interface, we can have surface waves that propagate, known as surface plasmon polaritons. These have again, an oscillating electromagnetic field. The magnetic field is coming in and out of this cartoon, but then this wave is also dragging along these conduction electrons from the metal. And what's nice about these surface plasmon polaritons is that they are confined very tightly to this interface, so within 100 nanometers, typically, of this metal-air interface. So I'm going to talk about each of these types of modes today, mostly on the plasmons. So I'm going to call them either surface plasmons or plasmons for short, just to abbreviate this three-word thing. But now, after kind of setting some of the stage, let's talk about the pixel. So we all know what a pixel is. I thought when we started this project, it was interesting to look a little bit into where this word comes from. And there was this very nice review article by R.A. Lyon from 20 years ago now about the history of the word pixel. And first of all, it stands for picture element. You may not be aware of that. And this was first used, according to this article, in the late 1920s, in this magazine article where they were basically describing to their reader all the amazing television technology that was being developed at that time, the early days of television. And then it was abbreviated to pixel. There were actually several competing abbreviations, but pixel, of course, eventually won out. And Billingsley, in a report from the Jet Propulsion Laboratory in the context of digital imaging processes in 1965, was the first written use of the word pixel. Here's Billingsley here in his everyday wear of this nice tie and white shirt in the 60s. And then in 69, it appeared in a Science magazine article about the Mariner 6 mission of digital imaging mapping of Mars. And then it kind of came into the digital cameras as they were developed. So at Sony, it was applied to the CCD unit cell for the first time in 75. And then in 82, Hitachi researchers used it in the context of digital cameras. Now, of course, today you could stop anyone on the street and ask them what a pixel is, and they would all know this, so it's ubiquitous. And that's because we have all of these pixelated devices around us. We have camera sensors, of course, that detect intensity. We have displays that are emitting intensity with control over each pixel. And then a third device, which is important to many of us that do optical spectroscopy research that you may or may not be aware of, are these spatial light modulators. So they are also pixelated, let's say 1,000 by 1,000. They're liquid crystal devices. So at each pixel, you use the liquid crystals and apply fields to affect the phase of the light that's hitting that pixel. So, but if you think about the devices we have, which of course are amazing, I mean, the digital cameras that we have now are amazing, but the pixels are only manipulating one of these parameters that I showed in the second slide. And so these two cameras and displays are affecting intensity, either generating or sensing intensity, and then the spatial light modulator is affecting phase. So what approaches could we think of to make more powerful pixels, multifunctional pixels? And the approach I'm going to tell you is not the only one that people are thinking about. So what we're going to try to look into is, can we use light interacting with surfaces to make new types of pixels? And so let me start a little bit from the beginning here and kind of set a picture that we're going to use to understand things. So that plane wave that I showed you in the second slide, of course, I mentioned that it has a wave vector that points in its direction of propagation. The wave vector has a magnitude, of course, is 2 pi over the wavelength. And more importantly, for what I'm about to say, for the single photon, the wave vector is also directly proportional to its momentum. So the wave vector is very useful for many reasons, but also because it's telling us about momentum. We know momentum is conserved, and so we can utilize that fact. So if this light wave hits an interface, flat interface between two materials of different refractive index, and we consider the in-plane momentum, the projection of this k vector in the x plane here, then in reflection, we know that the angle of incidence equals the angle of output, and this is simply to conserve the in-plane momentum, the x component, x projection of this wave vector. Similarly, in refraction, if the light enters a higher refractive index material, we know by Snell's law that it will bend towards the surface normal. And this is, again, simply to conserve the in-plane wave vector. So in-plane momentum of these photons on these flat interfaces is conserved. And this makes sense because nothing is changing in x for these structures. So why would its x momentum change? So they're x invariant. Now, this, of course, immediately becomes more complicated and more interesting if the interface is structured. And this is where diffraction comes into play. So a classic example of a diffractive surface, of course, is the diffraction grating, is shown here in this cartoon, cross-sectional cartoon. So we have a metal surface and periodic grooves. Then we know that when light hits this interface, that its direction can be altered by diffraction, but essentially it will boil down to constructive and destructive interference. But we can also look at this in a very nice way in terms of momentum conservation. So the grating will have a period, capital lambda, which gives rise to what we can call a grating momentum vector g, which points in the direction of the periodicity of the grooves, in this case x. And it has a magnitude, this grating momentum vector g, 2 pi over the period. And so again, we consider the conservation of in-plane momentum. In addition to the reflection off of this grating, or what's called zero-order diffraction, where the in-plane momentum is simply conserved, we will also, in first-order diffraction, basically add or subtract a unit of this g. So the diffraction is quantized in the units of this vector g. So if we add a unit of g, the light will diffract along the interface. And if we subtract a unit of g, light will diffract towards the surface normal. And of course, these angles are wavelength dependent, and that's why we can use gratings in spectroscopy. But this simple picture here is really useful for describing diffraction because we can boil it down to this simple momentum conservation picture and talking about these momentum contributions from the grating, these g vectors. So this picture then can immediately answer simple questions like, can photons launch surface plasmons, meaning let's say we have a metal film and we send a photon with a certain amount of in-plane momentum because of its angle, the projection in the plane. Can we launch one of these surface plasmon modes that has all x momentum? Does that happen? And to answer that question, we can look at the so-called dispersion diagram of the photon, so its energy on one axis versus its in-plane momentum on the other axis. And this is a useful diagram because both energy and momentum are conserved. So if the photon comes in at some angle theta here, then of course it will have an in-plane momentum that we can use to try to give a kick to launch a surface plasmon. And the maximum amount of momentum that this photon can give is along the so-called light line. That's when the photon is basically skimming the surface and theta equals 90 degrees. Now, it turns out if you solve Maxwell's equations and you figure out the solutions that are known as surface plasmon polaritons, they need slightly more momentum. So they need a little bit more momentum from the photon that the photon doesn't have. But now we can use diffraction to resolve this problem and add a grating so that we can send in light at an angle. So its in-plane momentum is, let's say, somewhere over here. And then match the momentum, the photons along this red line here, plus the grating momentum can launch a plasmon. So they have both the energy and then the momentum to launch a plasmon. So with gratings or diffraction in general, then we can make up for momentum mismatches, and this is going to be important as we go along. So now we have the question of, can we use diffractive surfaces in general to make this new class of pixels? And we have these key parameters for these diffractive surfaces. They're going to have some kind of periodicity that's going to be important, because this periodicity gives rise to these momentum contributions that are basically changing the direction of the light, and that's what we're trying to control. So the spatial period sets the momentum contributions, and just by units or the physical intuition, these grading momentum vectors, as I've described them, they're also 1 over length. So they're a spatial frequency. So the finer features you have on your structure, the higher spatial frequencies you'll have here, or the bigger the momentum kick you will get. And all of this that I've just described is very nicely described in Fourier optics, which connects the surface profile of my diffractive surface, basically how this corrugation goes up and down as a function of x, and these g's that are going to come out of diffraction. So the momentum contributions are connected to the surface profile simply through a Fourier transform. If you take some complicated diffractive surface that has some profile and you take the Fourier transform of that, it will give you all the Fourier components that tell you which momentum contributions you'll get in diffraction. Okay, so everything I've told you, very well known. What is the problem? The problem is kind of a trivial one, is that when people have been playing with these diffractive surfaces, all of these structures that people make are usually lithographically etched. So something like this electron micrograph I stole from this grading company, meaning that the surfaces are typically binary, meaning they have an upper level and a lower level, because the surface is either etched or not etched. So we have etched grooves and we have non-etched kind of higher areas. And it sounds stupid, but this really limits what we can do with diffractive surfaces. Because these binary surfaces, let's take a square wave grading. We can write the surface profile or height profile as a function of x of this square wave grading as simply a Fourier series. Again, using this Fourier transform idea that I said before, we can write the height profile out as a sum of cosines, each having a momentum contribution g, an amplitude a, and then some phase. And so while our square wave grading will have the fundamental spatial frequency that we probably care about, it's going to have many more to make these sharp edges, and those we might not want, and they might mess up our diffraction. So they're going to give these extra spatial frequencies are going to give unwanted contributions to diffraction. And maybe more important is if you only have a binary surface, there's only so many desired spatial frequencies you can add and keep it up, down, right? I mean, there's only so much you can do. And this problem of the limitations of these surfaces has been known for many decades, and there basically has been a lot of work over the last 20 years or so to resolve it in different ways. The most famous one to make better diffractive surfaces is through these so-called metasurfaces, which an amazing amount of work and advances have been done. And these metasurfaces are basically thin layer devices where you basically make many tiny little binary blocks. So you say, okay, I'm going to live with binary surface structures, but I'm going to make each individual structure much smaller than the wavelength of light. And then these little blocks will act as nanoscale optical resonators, such that when the light field comes in, it interacts with this resonator and it affects locally the light's amplitude, phase, and or polarization. And then by putting many of these together and orienting them in a certain way, you can do all kinds of amazing things to the wavefront of light in a thin optical device. And so this was first done here by the Capasso group, but many groups, including theirs, have gone on to show broad application of this for all kinds of very thin optical elements. And also many multifunctional devices. I'm just going to show one that I particularly think is cool that kind of gets us toward this multifunctional pixel device, where the Capasso group showed a polarization camera. So here's a metasurface that they made at the larger length scale. So this is 1.5 millimeter diameter. And then it's made of these tiny little blocks that are, I think, 300 nanometers across in the long cross-sectional direction. And then what they designed this metasurface to do is that if you project an image onto this, of this tree and a car and a little shrub, this device basically makes 4 copies of this image of the tree where it separates out different polarization components. So these circles here are like circular or near linear polarization components. And so then this can be used as this metasurface can be used as part of an imaging device where you then project these 4 images onto 4 quadrants of a conventional camera sensor. And you then, at each pixel, will get information about intensity, but also now polarization state of the light. So just one example, and like I said, many other metasurfaces have been pushing towards these types of devices. But I would also argue that there are some significant limitations of metasurfaces. So despite the amazing progress, there are several serious challenges. One is the fact that I said you want these blocks to basically be much smaller than the wavelength of light, but that one there was 300 nanometers. So obviously it's not much smaller than the wavelength of light. It's kind of smaller than the wavelength of light. And so it's basically approximating, we basically have said that light waves come in and they see the Fourier components or the waves in the surface profile. And so metasurfaces are trying to approximate that with these discrete structures, but they're still discrete. So this is an approximation, and the bigger these blocks are compared to the wavelength, the worse this approximation is. Maybe the bigger challenge, and the one that you don't really appreciate until you start working with metasurfaces, is how difficult the design is. So how do you come up with this crazy pattern here to make this device? So called the inverse design problem, where you know what the device should do, but you don't know where to put your blocks. And it's not trivial. And so these groups that do it for a living, they make these resonator libraries of what each little block does, depending on its size, shape, and orientation. But there are both local interactions with the light. So light comes in and interacts with that one block. But then they're non-local, meaning that the behavior of this block depends on its neighbors. And so that really makes it complicated, and it leads to a very computationally intensive, iterative process in the design. It's not trivial. So we started thinking about, well, is there an alternative approach to make better diffractive surfaces? And then we're going to move on to try to use them in pixelated devices. So the alternative approach is to not just assume that you can live with binary surfaces, but make something that actually only has the Fourier components you want in the interface. So basically, if you want 3 different Fourier components or sine waves in this surface, you just make that structure. This would, if you really had such control to make an arbitrarily wavy surface, you could add as many desired spatial frequencies as you want, where you control each of their amplitude and phase to do what you want, and also eliminate any unwanted spatial frequencies because you don't have any of these sharp edges that are giving all of these unwanted components. And the question when we first started this is maybe this will lead to more sophisticated diffractive surfaces. And so the big challenge is how to make this. I mean, the reason that nobody did this is because it's not trivial to make such a structure. And we were fortunate enough to have a new commercial tool in our clean room that was originally developed at IBM, known as thermal scanning probe lithography. And it's really an amazing tool. And we didn't develop it, so I just want to be very clear about that. How it works is it's a scanning tip technique, a scanning probe where you heat a tip to like 1,000 degrees, nanometer scale tip, and then you bring it close to a thermally sensitive polymer film and basically raster scan this tip across while you're controlling its height. And you basically carve out a surface profile in this polymer film that you desire. And since it's a fancy AFM, you're basically also measuring topography as you do this for feedback. And so it's an incredibly precise tool. In the hands of the people that developed it at IBM Zurich, they demonstrated sub 10 nanometer spatial features in the plane XY. Maybe in our work, we've basically not been able to go below 30, but we don't really care about that dimension. What's more important for us is you get incredible control of the height in Z away from the interface. So I'll show you in a second an error over a surface of just a couple nanometers in the height. So a very powerful, flexible approach. And so we used it to start making these wavy Fourier surfaces. And so the process is really simple. You have an analytical function for what crazy profile you want. You turn that into a grayscale bitmap, meaning at every position on this bitmap, it tells the tip how high or how low it should carve out the polymer, and you feed this grayscale bitmap into the tool. So a simple example, let's imagine you just want a height profile. That's just a simple sinusoid or cosine here that varies in the x direction with an amplitude a, spatial frequency g, and phase phi. So you take that function, you generate a bitmap looking down on what would be the surface. And so it's periodic going up and down in x, and it's constant in y. And so Nolan Lassaline, who started this project, then put this into the tool, and he made the polymer, wavy polymer. And so this is the measured height profile of this polymer film. You can see it's periodic in x and constant in y. And you can then look at the cross-sectional profiles, and I could just blow this up a little bit so you can see it. And hopefully you can see there's a red line here, which is the functional form, and then the blue open circles are the data. And you really get very nice reproduction of the pattern that you wanted. And in fact, if you take the average height error over this whole surface here, you get a value, like I said, less than 2 nanometers. So you have very high fidelity patterning capabilities. Now, so far, this is in a polymer, and of course, we want to use interesting optical materials. And so I'm going to skip over a lot of work, but we've basically developed techniques to make this in different metallic and dielectric materials. There are different approaches. One that Ferry mentioned is really simple template stripping. You take that patterned polymer and you deposit, let's say, silver on it, which is what I'm going to show you later. You stick a glass slide to the backside of the silver and you peel off the silver from the polymer and flip it over, and you have an inverted replica of the original polymer. And you can use the polymer then many times. Another approach that we've also utilized is simply etching. So you start out with the polymer as an etching mask, and then with anisotropic etching, you basically can transfer that into the underlying blue material here, which is what you want the final structure to be in. And which of these two approaches really depends on your mood or what you're trying to do. The template stripping is just unbelievably, stupidly easy and still works really well. But the etching also has some other advantages. For example, if you want to transfer it into single crystal and silicon wafer, you're going to have to etch into, you can't deposit that material. Etching is painful sometimes because it needs optimization, but you can also amplify the depth of your pattern, you see here, during the etching chemistry. So if you need deeper structures, you can also utilize that. Okay, so because of all of this, again, skipping over many things, we demonstrated silver, gold, silicon, silicon nitride, titania, hexagonal boron nitride, and lithium niobate Fourier surfaces by using various tricks. Just to show you 2 examples before we get back to the pixel story. This is a silver grating that we've added 3 sinusoids, overlapped 3 sinusoids. So here is the cross-sectional pattern, and we chose these 3 sinusoids, right? So you have complete control over what this pattern looks like. Or here's another structure using the etching into silicon, where we, just for fun, we overlaid 12 sinusoids. Each one is rotated in plane by 30 degrees, and you get this crazy quasi-crystalline pattern. What's cool is no matter how complicated it looks to our eye, you send in light, and of course math works. So it only sees the Fourier components. So in this case, it only sees the 12 Fourier components we see in it, and that's what would control the diffraction. So in that sense, the diffraction is really controlled as we would expect by these Fourier components. Okay, so now this was all maybe 5, 6 years ago, and so since then we've been thinking and working a lot of what we can do with these Fourier surfaces. The first thing is kind of trivial. We can make better diffraction gratings, of course, or at least we wanted to try to do that, because you can make a perfect diffraction grating, not the square wave grating that I said has problems, but just a single sinusoid, and send light in at normal incidence. And for first order diffraction, you would expect half the light goes to the right and half goes to the left. And we wanted to test this and see how efficient these new types of gratings could be. And so Nolan made such a structure. He had to make it deeper for us at the time. That was a challenge. Now it's not a challenge anymore. And then he measured the diffraction efficiency. So this diffraction efficiency is a function of wavelength. Ignore this dip here. This is due to coupling to plasmons, which wasn't important for what I'm about to say, but we'll get to in a second. But if you look out here in the red, basically, as you would expect, half the light is going to the left and half is going to the right within our experimental error. Maybe what's more interesting is since we control the Fourier components in this surface, why not do something more complicated and say, I want all the light to go to the right. What structure do we need? It's been known for decades that if you take the sawtooth grating, this does this perfectly, 100% efficient all to the right. And so Nolan took the first two Fourier components of such a sawtooth grating, made that structure, and indeed he could make all the light within our experimental error go to the right and none go to the left. So what we learned is we could make really efficient, very nice diffraction gratings with this capability. And that is important for some integrated photonic applications, especially where you're at the single photon level, which is a big thing. You don't want to lose any photons. So you want the most efficient gratings that you can make. But we were also a little bit disappointed, like making a better grating, okay? So we were really looking for more sophisticated applications, sophisticated in quotes. And then this led to a really interesting question for a couple years. Well, when is wavy better than binary? Because you can do a lot with binary, obviously. And so just to show you an example, let's consider a very old topic known as photonic crystal cavities. So you take that slab I introduced earlier where light is going to travel inside this slab, and then you drill many periodic holes in this slab. And you do that because you make basically light that tries to propagate in this slab keeps diffracting backwards because of the periodic holes. So light can't propagate in this slab. And you fill in then a few of these holes and you try to make a little cavity because light can propagate in there and keep bouncing off of the holes. And so this is known as a 2D photonic crystal cavity. And for example, Noda's group has done amazing work of this starting 25 years ago. 20 years ago. And so you get this mode in the middle here where the light, if you look at the light field that bounces back and forth inside this little cavity, very confined mode. But one issue they ran into at the beginning is that if you look at the dispersion diagram, remember this surface profile here, if I take the Fourier transform, I will get all of these different sinusoids that make up this complicated whole array here. And if any of them exist inside the light line, they can couple to photons and escape, and so that'd be loss. So we want all of the modal components to be to the right of the light line so that they can't get out because of this momentum mismatch that we talked about before. And early on, they would calculate this, take the Fourier transform of such a structure, and they would see radiative components inside the light line, and that was lossy. So they would have a worse cavity. And what you would want to do then is try to minimize all of these components inside the light line and make a better cavity. And this is really trivial with Fourier surfaces. So you basically can just pick which Fourier components you have in your structure. So instead of having something that I just showed you where if you look at the effective dielectric function around here, you have these very sharp edges, or here's kind of cartooning cross section. You have sharp edges that give all these radiative components. Instead, you make some cavity that has softer edges. We have only the components that you want. So that the effective dielectric function here is as you wish, and you can show that you can exclude all the radiative components, and so you can make a much better cavity. And so we did this in an experiment in lithium niobate, and it may be hard to see, but this is a little wavy lithium niobate waveguide here along this whole length. This is a 10 micron scale bar, so it's wavy the whole length. They'll blow up the central cavity region. And so this is the waviness here in the lithium niobate, and then it's tapered to nothing, and then it tapers again. So it makes this structure I had on the last cartoon, and you get a little cavity in there that should be very good. And in fact, in our first or maybe second experiment, when we measured the cavity resonance at about 1550 nanometers, you get 160,000. So you can make these very, like, look at the wavelength here. It's like 0.74 and 0.78. So a very narrow resonance because you can really control how much radiation leaks outside of this cavity. And so this led us to kind of a design rule: when is wavy advantageous? And basically the conclusion we came is the structure has to contain features larger than the wavelength. So like this cavity, the cavity length is larger than the wavelength. Then we can do really well. Now, the caveat, to be fair to the binary people, Noda showed that even with binary structures, by playing games, you can soften the cavity and eliminate some of these Fourier components. So Noda showed that if you move the spheres, the hole slightly, or change the size of the holes right around the cavity, you can go from something like I showed you here originally to something that's softer by playing with the size of the holes and again exclude the radiation. So Fourier surfaces are not always great. Binary structures can be optimized, but I think first, they're much easier to design, as I'll show you in a second. And also, the more complicated the application becomes, the bigger the advantage for Fourier surfaces. And so we're working on several of these more complicated things. One is we're making photonic neural networks with diffractive surfaces with Fourier surfaces. And then I'm finally going to get back to the pixel question. This is the other example that I want to stress today. So we want to try to use these wavy surfaces now to create these better type or new types of pixels. And the concept is really simple. We're going to exploit these propagating surface modes on a plane. And in particular, we're going to focus here on surface plasmons, but we wouldn't have to. And then we're going to have the following type of device where we're going to have a silver surface because we're going to use plasmons. We're going to have a source of plasmons that launches them towards some wavy diffractive thing we'll call a Fourier element, and then this will create some desired output. And this approach, and this wasn't completely clear to us at the beginning, immediately has several really nice advantages. One is these surface modes, even if they're generated by an incoherent source, are coherent and can propagate efficiently across the length scales that I'm talking about. These surface modes are dark because they have this momentum mismatch with photons, so you don't get any light from these plasmons until they hit the thing that we control. And so this means the output is completely background free. And then finally, and this is the biggest thing, and it's so beautiful from a mathematical sense, the design of this Fourier element, this complicated thing, is trivial because all it is the inverse Fourier transform of what you want. So you take some desired output field, you take the inverse Fourier transform, and it tells you the surface profile you want, and then you just have to make it. And we have this tool that can make it. So you can then generate complete control of the optical field. And so let me just show you a few examples, starting with something really simple. It's called a vortex beam. It's basically a beam that has a phase front that's basically spiraling or twisting around. And here's the structure in a cartoon that will do this. Our source of plasmons now is going to be the grating on a silver structure. We're going to send in light and generate plasmons. So we have the grating. We have a Fourier element that's going to make this vortex beam. Light goes in, creates plasmons, and then should generate the desired output, which should be this spiraling phase front that I mentioned. And so you take the inverse Fourier transform of this thing you want. You get this height profile, which kind of looks like a grating with a little dislocation in it. And then you make this an experiment with the thermal scanning probe lithography. Looking down on it, here's the grating that will generate the plasmons, and they will go to this little fork region. The other advantage we didn't really expect, but these things can be very, very shallow and still be very efficient. So it's really even hard to image them in the electron microscope, but I can blow this up, and this is the highest region of this surface. And you can then measure the output from this structure that I just showed you in an optical microscope. So this is this vortex beam that's being projected onto the microscope. And you get this little donut beam because of the phase singularity in the middle. You can't have any intensity where the phase can be anything in the center. And then you can go on and you can make a structure that doesn't have one twist per wavelength, but 3 twists per wavelength. You get a slightly bigger donut. 5 twists per wavelength, get an even bigger donut. And just to confirm that you have exactly the amount of twists that you want, you can use this trick where if you send this beam through a simple cylindrical lens, the interference pattern basically has black nodes. And if you just count the black nodes, it tells you how many twists you have in the beam. So that's maybe a technical detail, but you can really confirm that you're getting exactly what you want. Other examples, this structure here projects an ETH logo, so you can make very flat field holograms, better as far as we can tell, than any meta surface because of this control that you have, or a different structure, not this one, not this one shown here, but another structure could project multicolor ETH logo. And then you can play with your imagination here. Those were all projected at the far field, but you can also project at any intermediate plane. So this structure was designed, has a grating, and then this is the Fourier element that focuses to a single point 25 microns above the surface. And when you go and look for that point, you basically get a diffraction limited focal spot. So you really have a lot of control of what you can do here. And then finally, on the generation side, you can control the polarization. So so far, I just showed you phase and amplitude. But if you combine two gratings and you utilize the fact that these plasmons have fixed polarization, you can send light from these two gratings towards a 2D Fourier element and generate an output. And so, for example, you can send in light here that generates an X component of the output that has polarization, basically left or left up or right down, or you can send in light from this left upper grating along the Y direction, and then you can, of course, superimpose both of these at the same time, and since everything's coherent, you can make this donut mode where the polarization is basically rotating around the axis of the beam. This is called a vector beam. And so here you can, again, project it on the microscope, and now with a polarizer, by rotating the polarizer around, you can see that indeed you have the polarizations you expect in this vector beam. Okay, so the bottom line is that you can do basically anything in the generation. You have complete control over what you generate from these pixels. But now let's do the reverse, which is a little bit harder. Can we sense arbitrary fields with the same platform? And if you've ever tried to use a phase camera, so a camera that can detect phase across it, they are horrible. So it's not an easy thing to do, but it turns out with these little Fourier elements, you can get incredibly sensitive phase pixels. And the idea is kind of following from what we had before. Now you use a structure where you have two gratings, one on the left, one on the right, and you want to measure the phase difference phi in between light that's landing on the left grating and light that's landing on the right grating. So in other words, you send in an A beam that excites plasmons moving from left to right towards the Fourier element, a B beam that has a slight phase difference from A moving from right to left, and then you have the Fourier element that diffracts these together at some angle, but the Fourier element that, of course, we can control and design adds an angle-dependent phase difference between A and B. So that means as you change theta, at some point they'll be out of phase in the output plane, and you'll see a black line. So this is how the output phase changes. It goes up and down as theta gets bigger. So that's what the Fourier element is doing. And so the output, you basically get these streaks where you basically have two black lines, and from that you can read out, we put in a known phase difference between A and B, and then looked at the output image, and you could read out what the phase difference was. And in fact, these sensors are so sensitive, we can't make a phase field that's good enough to really test it. First, you just tap on the laser table and the output of the sensor changes. And also we were seeing fluctuations, and we tracked it to the 0.07 degree laser pointing instability. So they're just incredibly sensitive because they're on a small scale, and you can make these structures so precisely. That's phase. Polarization sensor is a little bit more complicated to explain, but I'm going to try. So if you really want to know the polarization state of light, you need these 4 Stokes parameters. So let me just remind you or introduce to you what those are. The first one is just the intensity of the light. So you can take horizontal and vertical polarization and add those, and you will get the intensity. Then you have the degree of basically X and Y linear polarized light is the difference between those. That's the second one. Then you have the degree of basically diagonally polarized light. That's a difference between plus 45 and minus 45. And then you have the degree of circularly polarized light. And usually in the lab, to measure these, you would be putting all these half-wave plates and polarizers in there, and you'd have this really bulky object. This sensor can do the same thing. So this is a little Stokes polarization sensor. It has two gratings because light that comes in with X polarization here, so this will be En dot X, will launch plasmons towards this Fourier element. And then the light that comes in that has a Y component will launch plasmons from this grating. And these two will interfere and diffract off of this thing, which is designed to do the following. And I'm going to try to do my best here to keep you coming with me. It projects two images, just two rectangles. That's all it does. The X component projects a rectangle in the output plane that has constant phase. And then the Y component has a rectangle where I add phase either 0, pi over 2, pi, or 3 pi over 2. And then when I add these and superpose these together, I get regions that I can use their intensity to basically back out all of these. So this is basically what we're doing is adding these half-wave and quarter-wave plates to these different regions of the rectangles. And so by reading out this image, we can extract the Stokes parameters. So to show you an example, we send in light that's diagonally polarized. This brown box here should light up, and it does. That's this one right here. And the orthogonal one should be dark, and it does. So with this type of image, you can extract out the Stokes parameters, and this one here, degree of diagonally linear polarized light should be 1. It's 0.87. If you send in right circularly polarized light and do a similar experiment, this should be -1, and it's 0.83. So, and again, our ability to send in a known polarization is really limiting us here to push these sensors. So we've really been limited so far by our ability to create in our microscope known polarization state. Okay, and then the last thing I want to do in the last couple minutes here is now let's really try to put all of these things together in a single pixel, because this platform allows us to do this. So the first approach, which now in hindsight is really stupid, but let me admit to that, is you simply make sensors next to each other that do all of this at once. So you have a Stokes sensor, then you have a phase sensor that tells you the phase differences along the X direction, so a phase gradient in X, and then you have an X sensor, a phase sensor for gradients in X. And then you design, because you can design the output any way you want, you design it so that on the edges we get the phase sensors. So these are just redundant, two of these strips that the dark nodes tell us the phase, in this case in X, and then this in Y, and then we place the Stokes sensor in the middle, just like I showed you before. And you can use this to image all kinds of things. But the reason it's stupid is because all the math I told you about is linear. So why should we make 3 separate devices when we can just superimpose all of them together and make one pixel that does it all? So kind of like the one pixel that rules them all kind of concept. So the second approach, which we think is much cleverer, is you just take the surface profiles for each of those 3 things and you combine them into, you just mathematically add them, and you can make that structure. And now we have to have gratings on both sides here. And the layout's a little bit different because of the design is a little bit different for the Stokes sensor, but still it's basically the same. So you have the phase sensors at the edge of the image, output image, and the Stokes sensor is in the middle. And this is 40 micron by 40 microns, this central Fourier element here. And of course, you can go smaller. So if you go down to 10 by 10 microns, which is now really starting to become kind of the size of a conventional pixel, you lose some resolution just because finite size effects. But there are also tricks you can play to keep the size smaller and increase the resolution by basically putting a high refractive layer like alumina or something on top of this structure. And so the last slide, we've just used these types of sensors to image different kinds of profiles. So this is the phase image using this single pixel to scan over a vortex beam with a twist of +2. This is the phase profile. or a certain type of beam that has this so-called trefoil phase aberration. And then this is what we would expect, but also what we measured. And then we've also been imaging different polarization. So there's a vector beam with basically one twist in the polarization, and you can measure the polarization direction around this image. And this is really just the beginning. So we just submitted our first paper on this, and there's just lots of different things that one can imagine. For example, you could even imagine a pixel that's a little Fourier transform infrared spectrometer, right, in one little object, right? So you can start playing with a lot of things. Okay, so to conclude, these Fourier surfaces in general can enhance properties of diffractive elements, and they can outperform binary surfaces in gratings, couplers, and holograms, although binary surfaces, in fairness, can sometimes be optimized. Beyond gratings, we wanted to know when wavy is better, and we've been looking at optical computing, although I didn't talk about that. I took those slides out. But now we're looking at its ability to make pixels for reciprocal light control. In principle, you can do both. It can sense and generate, and maybe in a single package is something we're working on now. And also, I didn't mention it, but they're very efficient. So like that, those devices are 40% in, power out. So it's not like you're losing all of the power that you're sending into these devices. And then finally, let me just acknowledge the people that did the work. I mentioned Nolan a couple of times. He's really the driving force behind the Fourier surface project. And then Yannick Glauser and Sander Vonk really pushed the Fourier pixel project forward. We had help from the tool manufacturer, Swiss Litho, now Heidelberg Instruments, Martin Spieser and Samuel Bissig, and help from IBM, Armin Knoll, the father or developer of the thermal scanning probe lithography at IBM Research. And with that, let me thank you for your attention. I'll be happy to answer any questions.
Hey, thank you, David. Please, questions from young people in the audience as well. We always stress this. We can go ahead first with Stefan. It's not a problem.
Sorry not to be young. It's not my fault. Thank you for your talk. It's very interesting. And I'm going to take your last words, which is, this is only the beginning. So
Yep.
What's coming next? And I would like to know if, even though it defeats the purpose, your pixel, it's made of pixels, like it or not. And what's coming next could be a dynamical superpixel that you control with smaller pixels that makes something that you can tune and change and make it. Do you have an idea how to go to that point?
So we have lots of ideas which ones are going to work. I mean, it's a big challenge. And really we have to, since we just submitted this 2 weeks ago, we just kind of took a break over the holidays, and we haven't, as a team, we haven't discussed, because we worked like dogs for the last 3 months. We really have to think about exactly how we're going to approach that, because you could switch completely from silver and go an integrated photonics approach, where you have waveguides that are going to Fourier elements, and then you control the inputs to all those waveguides, and you could use integrated photonics. That's not really our area, but this is something that we could think about doing. Or we could stick with our current platform and think about ways that we can control the output. But making it dynamic is clearly a goal. Or, as maybe you alluded to, you have many fixed pixels on your little super pixel, as you called it, and then by changing which output you have, you can control the overall output. One thing that was kind of motivating us, maybe it's stupid, is this kind of Princess Leia 3D hologram from R2-D2. This is in principle possible with this approach, where each pixel that you make would take one slice of this hologram, and this is something that we're going to try. If you don't hear about it in the next few years, then it was a complete disaster, but otherwise we'll show this.
Hi, thank you for the very nice talk. I believe you've mentioned how it doesn't matter how deep the etching is when it comes to the performance of the pixel. But if that were really the case, pays off to just make it as deep as possible, since then the relative error in the height is going to be lower, right? So my question in the end is there really no drawback from amplitude?
So first of all, maybe I misspoke, but it's not that the depth doesn't matter. So there is an optimal depth for these on silver, for these Fourier elements. It's just that it's pretty shallow. So it's on the order of 100 nanometers max that you need. And then there's lots of serendipity in this project. There was a lot of luck in the sense that this thermal scanning probe lithography, when it works best, is when your patterns are relatively shallow. So like 100 nanometers is like almost right in its sweet spot. So then it's not the relative error. It's, I mean, as the structures that it's trying to write get deeper, the relative error actually gets larger. So, so it was fortunate that exactly where the tool can make very precise structures is the depth that extracts with very high efficiency the light out. And also like the gratings are incredibly, like 80% of the light we can launch in one direction by playing with this input grating. So you don't lose almost any light that way. And going back to the earlier question, another thing we want to do is maybe not come in from the top. It makes the experiments really complicated because you're going in and out from, you got to mask everything in the microscope. And if we make a slit and just do it in transmission, we can generate the plasmons by the light that comes through the slit, and then we'll just see the output from the pixel. Sorry, I tacked on something else I wanted to say to your question.
Thank you.
This IBM method of etching plastic sounds rather slow.
Yeah.
Are there other methods for high throughput that are on the way?
Yeah, so it's a good point that this thermal scanning probe lithography, to make such a structure is like 10 minutes of writing time. So it's certainly not going to mass produce it, writing them one by one. You can then take that, as I mentioned, and replicate it many, many times. And there are mass producible ways that one can do that. And we've played a little bit with that with this nano imprint lithography. One can imagine, I mean, we're an academic group, but one could imagine that one does this. A bigger dream that I have, but it's not quite there yet, and we don't do this. There are all these groups that are making Fourier surfaces by overlaying beams of light in these azobenzene polymers, which have this crazy behavior that they move around in response to the illumination pattern. So there have been groups that have, after our paper came out, made much larger scale Fourier surfaces with that technique. It's just that the control they have is not quite as good, and the periodicities that they can get to is still limited. But I'm really betting that they're going to make that better, and then we can make these kinds of structures over a whole wafer if we want to.
This kind of device that you're showing have in-coupling elements and out-coupling elements.
Yeah.
And out of the same idea you have mentioned before, wouldn't it make sense to incorporate both the in-coupling and out-coupling in a single profile so that you reduce the size of your device?
Maybe I don't understand the question. This device here has both in-coupling and out-coupling.
You have the gratings to couple in the light, and then you have the spot in the middle, which has 3 different functions.
Yes.
But maybe you could even, in a single spot, have both the in-coupling and the out-coupling, and you cut down the size of the device.
Yes, it's a good thought. My intuition is that we're going to have a problem there, but I don't have a good reason why. So yeah, we'll think about this. I'll think about it.
Thank you.
And how do you, how do you extend this to light detection? Now you're producing light with it, but if you to detect a complex light field.
So this device here detects the complete state of light. It uses a conventional intensity detector to read out, but this tells us all about the phase gradients in X and Y, the phase profile, and the polarization state, and the intensity. So with that 1 pixel, it detects for the light that lands on it, its complete optical state.
Well, it seems we all make questions in this area. So has anybody thought about or analyzed what is the trapping force of these surfaces and try to, because with this technique in principle, you could do any landscape of potentials and even try to mimic some or simulate some solid state physics with trapped particles in this.
Yeah, so I have 2 colleagues, Lucas Novotny and Romain Quidon, who do this. And so they've been interested in this. We haven't done anything yet because of the reasons I was saying before. But this wasn't even the tightest focus we could get. Because depending on where you put the focus, you get a larger NA. And so I think 0.8 was the largest NA that we got, and it was sub 200 nanometer spot in the way that we measured it here. So and also we made other structures I didn't show where you can make an array of these foci. And so, yeah, we haven't done anything, but definitely there would be a trapping potential and you could play with that. And it seems interesting to me. But if you want a structure to play with, let me know. We'll make you one.
Thank you.
So at the end, the surface plasmon propagation length, even though this is, as good as it gets in terms of silver, you still have a distance dependence once you get to your central element, right? So is there any correction factor that you need to put in that maybe in the center you need to have somewhat more intensity, sensitivity, or something like that? Have you corrected for that, or are there any?
Only in really trivial ways. I think and then probably not this one, but or maybe this one, at certain transitions, we've apodized the Fourier element so that there's not a lot of reflection back. But yeah, we've been talking about this a lot. There are a lot of things that we could do to optimize this because you're right. I mean, on a few tens of microns, the plasmons are losing intensity, and you could correct for that in your design. It makes the design more complicated, and right now it's just mathematically amazingly beautiful. And also, if you went to photons in a slab waveguide geometry, you would have other disadvantages, but one of the advantages you wouldn't have is these types of propagation losses.
And so this is very, very interesting because at the end, the intensity here in a focal spot is gonna eventually depend on the damage threshold of your structure. So if you could make, I mean, I don't know what is the limit of NA, theoretical limit of NA. If you could make a infinitely large Fourier surface, you could get very high intensities.
Yeah.
Is that is there any other limitation that needs to be taken into account?
So Munji Bawendi was just visiting me, as I told you earlier, and that was the first thing he asked me was what the damage threshold, and we haven't pushed that. But even if you melt the silver, you could then put like alumina layer on it, and I think the damage threshold would be pretty high, or you could switch to another metal that has more thermal robustness. Then the question, I mean, so far, our lenses like this just follow the curve that you would expect NA versus the spot we measure. So then it's just the limit of how big we can pattern these, right?
If you have a wafer, I mean, the NA becomes humongous.
Yeah, for sure. Yeah. But we wouldn't be able to make a Fourier element that's wafer scale at this moment. So that's what I'm saying, that we're limited by the size of this structure and then how far away the focus has to be.
Right. Any more? Stefan.
Following on this discussion, I don't see any problem with having arbitrary intensity because this is 25 microns above. So it doesn't affect the lens, in fact.
But I mean, you're sending in your light here. And so the concern, and we haven't tested this, is how intense can your laser be before you melt this grating?
I understood that the question was how intense that spot can be without affecting the lens, but this spot is far from the lens. So the light is spread all over the pixel structure, but it only focuses on a spot 25 microns above. Assuming that is the number there.
Yeah, no, that's correct. So it's distributed on the lens, just like any lens, the intensity is distributed before it's focused. But I think the ultimate limit of how intense this spot can be is what the damage threshold of the incoming input grading is. And it's silver, so I mean, silver can melt. And
I had an additional question. Have you ever tried circular grooves to launch spherical waves instead of plane waves?
We have not. I was thinking about that when I was preparing my talk yesterday. We have not. That would change the design slightly. We basically using these orthogonal so that we can basically orthogonalize the incoming plasmons. That makes the math really simple. But you could definitely go to a different basis where you have circular waves. And what that would add, I don't know. But it was something that I was also thinking could be potentially interesting. But it's also interesting. I mean, a lot of these patterns like this one, at first it looks kind of weird that this makes a focus, but after a while you kind of sit and everything. Of course, it's math works, but then you have to kind of come up with a physical intuition, and they always make sense after you think about it, that's what would cause the focus.
Not. I think, do it again, please.